In the last video, we looked at the moving average processes in a little bit more detail. And in this video, we look at the AR or the all-pole models in more detail. And this model or the AR model is obtained from the general ARMA model by assuming that we only have one feed-forward path active and then only the autoregressive part. So for the AR model, we know that the transfer function is given by B0 divided by this polynomial in the feedback coefficients and Z. And we can, as well as in the previous case, in principle, invert this transfer function in order to obtain the impulse response of this system and use that in our modeling. So there are a number of properties with AR models which make them useful in practice. So one of the reasons, or one of the motivators of AR models is that they can arbitrarily accurately model general ARMA processes, provided, of course, that we allow the model order to be large. So generally it has to be much larger than the corresponding model order for the ARMA process in order to accurately model a general ARMA process. However, one of the reasons why people are generally interested in AR models is that the parameters of the AR model, it will turn out, can be obtained from the autocorrelation via a linear system of equations. And this means that the parameters of the AR model is very easy to obtain once we have the data. Also, one of the things to look out for in the AR model is that since we have a recursion or a feedback, we need to worry about stability again, which we didn't have to do in the moving average models because an FIR filter is always stable. So, in the autoregressive model, the parameters are given by the feedback parameters A1 to AM and the feed-forward power gain B0. We can simplify the difference equations for the general ARMA model to the AR-specific case, and we would get the following model, where En would be the driving noise, which we again assume is white. One of the things one can show is that at time lag 0, the first coefficient of the impulse response will be identically equal to this B0. And this is because when a sample enters the system, it will immediately reach the output through the multiplication of B before it enters into the feedback part of the equation. And as noted before, we could simplify the Joule-Walker equations using this insight in order to obtain the following expression, which we can see is linear in the AM. So we have made the explicit dependence on the impulse response disappear from the right-hand side of the equation. So as before, we can use this equation for different values of k in order to set up a system of equations which we can then solve for the parameters AM. So the nice thing about this equation is that if we choose k as any other value than k equal to 0, also the right-hand side will disappear, and we have this left-hand side equal to 0, which is then purely linear in the parameters. So if you set up a system of equations by choosing k equal to 1 from 1 up to capital M, we create a linear system of equations that can be solved for the model order parameters. And that will be the Joule-Walker equations for the AR model, which we can then pose in matrix form as follows. So this is a set of linear equations where the coefficient matrix is defined by the autocorrelation of the observed process, as is the right-hand side, and we could solve this for the coefficients of the model, and that's equivalent to this. Then, if we're also interested in the B0 coefficients, which they typically are, we can obtain that by using the value of k equal to 0, which creates an equation that is easily solved for B in terms of the coefficients A that were obtained from the linear system. So all in all, this is a very simple way of obtaining the parameters in terms of computational complexity, because we do know how to solve linear systems of equations, and this is given in closed form. So the way to obtain an AR estimate is, like for the moving average, first to estimate the autocorrelation from the data, and then use that in order to obtain estimates of the parameters using the estimated autocorrelation process in place of the true autocorrelation function, which we do not know. So there are many different ways here as well to obtain estimates of the autocorrelation. But one thing to note here is that we need to be a little bit careful in how we choose the estimator for the autocorrelation function in this case, because if we choose it wrongly, we could lead to a set of parameters A, which leads to an unstable filter, and that would be a problem. However, one can show that if we obtain an estimate of the autocorrelation function, just as if we did in the periodogram, for values between 0 and n-1, which is the data that we have, then using that estimate in the way that we prescribed in the previous slide will always yield a stable AR process. And this is usually referred to as the autocorrelation method for AR spectral estimation. And this is the one that we will consider in detail in what follows. So in order to get a view of how well an AR spectrum estimator works, let's consider again our AR4 process with the power spectral density as we've seen before. And just as a reminder, the periodogram gave us an estimate looking something like this. We could improve upon the periodogram estimate by using other spectrum estimation methods as we saw before. So for instance, Bartlett's method, where we divided the entire set of data into several blocks and averaged over those. And one of the problems with that was that while it reduced the variance, it also smoothed the spectrum, giving us less resolution than for the periodogram. Or we could use the Blackman-Tukey with a certain maximum lag and with a pre-specified window in order to further smooth the spectrum and get a very low variance estimators, but again at the expense of a much widening of the peaks or a loss in resolution. So in this particular case, we wouldn't be able to capture the peaks of the original spectrum as accurately as we did with the periodogram. However, now if we look at the AR spectrum estimator, it uses, in this case, the fact that we know that the data that we're looking for is from an AR4 process. So we don't know the particular parameters of that process, but estimating those from the observed samples gives us an estimate which very closely matches the original process spectrum estimation. And of course, this would also be prone to variance, but this variance is quite low. So if we pull a new realization, we may get something like this. But in every case, it looks like a very good fit to the underlying spectrum. One way to understand what the AR parametric spectrum estimation is doing is to look at the autocorrelation that's produced by the estimator. So in this example, we have an autocorrelation function from an AR4 process, not the same one that we saw before, but another AR4 process that plots more well in terms of the autocorrelation. So what the periodogram estimate would do is it would look at the different time lags of the data samples, in this case 256 data samples, and average those in order to come up with an estimate of the autocorrelation function. And that may or may not be close to the true autocorrelation function, which is shown in black here, and typically we will have worse performance as we move out into the tails, simply because those estimates are formed by averaging over less terms. So the way that the Blackman-Tukey estimate improves upon the periodogram is to weigh down the periodogram estimate using a window. So we'll have a max lag for the Blackman-Tukey estimator, which would force our estimated autocorrelation spectrum to be identically equal to 0 past that time lag. And within the non-zero values, we would apply a smoothing window, which would suppress it towards the edges. And multiplying the autocorrelation function with the window, or the estimate with the window, is equivalent to smoothing in the spectral domain, and this reduces the variance at the expense of broadening of the spectral peaks. What the AR estimate would do instead is it would form a model based on our estimate of the autocorrelation function that we obtain from the periodogram estimate. So in the particular case, if we assume an AR4 model for our spectrum estimator, what it would do, it would choose the parameters of the model so that it matches the autocorrelation function for the first 5 samples of the estimate as obtained by the periodogram. And then past this value, it would let the model determine the rest of the autocorrelation function. So if we compare it to the periodogram estimate, which is now shown in gray here, and the AR4 estimate, which is shown in red, we see that the red AR4 estimate coincides with the periodogram estimate for the first 5 samples, so from 0 to 4, while afterward it may deviate. But it actually follows the true model, which is also in this case an AR4 model, better than the periodogram estimate. So extrapolating from the information contained in the lower order or lower time lag samples to higher time lag samples improves the performance. and this is what we see in the AR4 estimator. Now, one can argue that we have cheated so far in the sense that we have assumed that we know what the underlying process there is, and that this is the reason for why the AR4 power spectral estimator has done so well in the plots that we've shown so far. So in general, the important question is, how do we know that the process that we will measure is an AR process so we can apply the AR spectrum estimator? And how do we know what the order of the underlying AR process is so we can choose the order of the model? So in general, one can argue that the first one we will not know, but we can make a modeling assumption that it's an AR process, and then it's maybe based on tractability, or it may be based on physical reasoning regarding the process which generates the data sample, so the stochastic process that we observe. So regarding the second question of how do we know the order of the AR process, that's a topic called model order selection, and this is typically an important topic when you do spectrum estimations. You need to decide on which order of the model you should choose for your spectrum estimator. So in order to get some understanding of how the model order affects our ability to describe the data, let's again consider the AR4 process that we studied before with the true spectrum given by the black curve. And we've seen an AR4 parametric spectrum estimator based on 256 samples before, and this is the curve shown in red here. Now, if we in our modeling assumption used for the spectrum estimation assumes a model order which is lower than the true model order, then typically what will happen is that our estimator will not be able to describe the particularities of the data. So in this case, we are looking at an AR2 parametric spectrum estimator applied to the same data samples as before. And we see that an AR2 model simply doesn't have enough degrees of freedom in order to describe the characteristics of this spectrum, and therefore our spectrum estimator suffers in performance in this case. However, if instead of choosing an AR2 process, we choose an AR6 process, so in the sense we choose too many model parameters, then we are clearly able to describe the data, and we in this case don't suffer a lot by choosing the model order too high. So we are still obtaining quite an accurate spectrum estimator in this case. And we can take this further by moving the number of parameters up to an AR10 model, which again is well describing the true spectrum of the process based on these samples. We see some slightly larger deviation due to the fact that we now have more parameters that we need to estimate, and therefore the accuracy of any particular parameter suffers. So if we move up to an AR40 process, which is a lot of more parameters than that was used to generate the data of the underlying processes, and quite a lot of parameters to estimate from simply 256 data samples, then we see that again we suffer in terms of performance, in that our parameter estimates become very unreliable, and therefore for that reason we are not able to describe the true spectrum so accurately. But even comparing the AR40 parametric spectrum estimator to the periodogram that we started with based on these 256 samples, we are seeing that even the AR40 estimate is doing quite a good job in comparison to the periodogram estimate, although it's not doing quite a stellar job as the AR4 parametric estimator, where we actually hit the true order of the underlying model. So a question related to how the model order corresponds to our ability to describe a given spectrum. So assume that we have a given spectrum which exhibit 5 sharp spectral peaks. Then what model order would we have to choose for an ARM model so that the model is able to describe a spectrum having such 5 sharp peaks? So in general, the ARM model would have m plus 1 real valued parameters, so the constant gain plus the m parameters a1 to am. So how many of these parameters a1 to am would we need in order to be able to describe 5 sharp spectral peaks? Would we need 5 parameters, 10 parameters, 15, or 25? Well, the correct answer is option number 2. We would need 10 of the A parameters, so in total 11 parameters of the model, or we would need an AR10 model to describe a spectrum with 5 sharp peaks. And the reason for that is that the A1 to AM parameters characterize the poles of the transfer function of the filter underlying the autoregressive model. And we know that if we choose all these parameters real valued, then all poles would appear in complex pairs. And each spectral peak of a spectrum generated by the AR model corresponds to one such pair of poles. And in order to have 5 poles, we need a polynomial in the denominator which has an order of 10, and this is equivalent to the number of parameters that we need in our model in order to create 5 sharp peaks. And this is also consistent with what we saw before, that an AR4 process can have 2 spectral peaks, as we saw in the data in the previous examples. So in order to look at the second question of how well we can use AR models as a modeling assumptions, even if the process that we are trying to estimate is not truly an AR process, we can look at another example. So in this example, we have another process which is 2 sinus processes in white noise. So the white noise will give us a constant power spectral density across the range of normalized frequencies, and the sinus processes will give us sharp peaks or delta functions at the frequencies where the sinus processes contain their energy. So if we apply a periodogram estimate to this data, it would look something like this. So the periodogram estimate would be able to pick up on these 2 sharp spectral peaks, but it would have the problem of a large variance, which is what we've studied before. And in this case, we based the periodogram estimate on 256 samples from the stochastic process. We can improve the variance, as always, by applying other methods. So in this case, Bartlett's method, which would trade variance for resolution, as we've seen many times before. And we could still locate the 2 spectral peaks, but we get less variance over the part of the spectrum which contains noise only. Or we could apply Blackman-Tukey's spectral estimator to get a really good estimate of the noise level of this process. But due to the widening of the peaks, of the spectral peaks, due to the smoothing caused by Blackman-Tukey's method, we would in this case no longer be able to separate these 2 spectral peaks in our observed spectrum, which is given by the red curve here. If for this data we applied an AR4 process spectral estimator, we wouldn't see much variance in the estimator, but still an AR4 process, even though it's able to create a spectrum with 2 spectral peaks, would in this case merge these 2 peaks. But we could address this, the fact that the underlying process is not truly an AR process, by increasing the model order of our AR model, making it more capable of describing complex spectrum behavior. So if we increase this, for instance, to an AR10 process, we would see that we get an estimate containing 2 sharp spectral peaks, identifying the location of the spectral peaks in the underlying process, while at the same time getting a fairly decent estimate of the noise level in this area where we have noise only and no sinus components. So in this case, an AR10 model could be appropriate in order to describe or model the underlying data, even though we know that it comes from a different model, and it would lead to a reliable spectrum estimator. So to summarize, again, using signal modeling, as we've seen before, we can inject some knowledge into our estimation problems. So essentially we can assume that we know something about our signal. AR models are very often used for this purpose, as we've seen in this video. One of the reasons is that there are many processes in nature that you can argue come or satisfy AR modeling assumptions. So one typical such argument is made for speech coding in, for instance, GSM, where one argues that the vocal cord causes a reverberation which is similar to what is given by an AR model. So AR models are very often used for that. And the second big point of AR models is that the model parameters are very easy to compute from the estimated autocorrelation through these linear Yule-Walker equations, which makes the AR models a very computationally efficient tool to estimate spectrums, while still getting the benefit of a model-based spectrum estimator. So one of the problems which we haven't really addressed, other than by a few examples, is this remaining problem of model order selection. So what we've seen so far is that it's better to pick a slightly too large model than a slightly too small model, which means that we couldn't model our data. However, we also don't want to pick a too large model, because then we have too many parameters to estimate, and that will negatively affect our spectrum estimates. So in the next video, we will look at how to appropriately choose the model order and how to think about this problem.